Welcome students. In previous class we are talking about the topic that is electric potential due to a point charge, electric potential due to a dipole at an axial point, at an equatorial point and at any point. In this lecture we will be talking about an important relation, that is the relation between electric field and electric potential. So let's start. All of you know, if there is a point charge plus q and you have to calculate electric potential at point P, what will be the value? The expression of electric field at first, that is 1 by 4 pi epsilon naught amount of charge by separation the square. Suppose this separation is R. Now what is the value of electric potential here? The value of electric potential, that is 1 by 4 pi epsilon naught Q by R. In case of electric field, E proportional to 1 by R square and V proportional to 1 by R. In this class, we will discuss the relation between electric field and electric potential. So, let's start. Suppose there is a point charge plus Q. We consider an electric field E due to this point charge plus Q, which is placed at origin O. Okay. Now we consider two adjacent points, here A and here B, and the potential, electric potential at point A, suppose VA is equal to V, and at point B, that is VB is equal to V plus dV. Now, what will be the value of electric field here? Suppose there is a point charge Q naught at point A. So the direction of electric field, the direction of electric force, that's along x-axis, because this is positive charge, this is positive charge, nature is repulsive. So this is the direction of electric force as well as electric field. Now, suppose we are taking a point test charge Q naught from point A to point B, which is separated at a separation dr. This separation is dr. And we consider 2 points A and B are very close to each other. That is, if the point A and B are very close to each other, then you can say that the electric field E is constant, because both the points A and B are very close, so the separation, that is nearly equal. Okay. Now for taking a test charge Q naught from point A to B, what we have to done? We have to done an external work. Clear? And this external, we have to done an external force, not work. This external force, that is F external, result will be negative of electric force. So the result will be minus Q naught into electric field. This is the external force which is required for taking a test charge Q naught from point A to point B. Now, for taking test charge A to B, we have to done work done also, and this work done result will be dW, or you can say W, that is equal to F vector dot dr vector. Here external work done, which is directed along that side, clear, and dr also same side. So this expression will be F dr cos 0, that is F dr. Now putting the value of F, that is minus Q naught into E into dr. This equation given number 1. Again, if we taking a test charge Q naught from A to B, there will be another form of work done according to second chapter. That is, you know the formula, and the formula is electric potential V, that is equal to work done by test charge. So work done is equal to test charge into potential. but here there is a potential difference between 2 points. So we are taking a initial point A to B, so the potential difference will be VB minus VA. Now putting the value, that is W equal to Q naught VB value, that is V plus del V, and VA value, that is V. Here V cancel out, and the expression of W, that is Q naught into dV. This is equation number 2. Mind it, one important point here, when taking a test charge Q naught from A to B, there will be a zero acceleration. That means the velocity remains constant. We have to take the charge Q naught very slowly from A to B. That in that case, there is the constant, the kinetic energy, the change in kinetic energy value remains constant. Okay. Now equation 1, that is expression of W. Equation 2, that is expression of W. Both of the expression, that is work done for taking test charge Q naught from A to B. This expression is represented in terms of force and displacement, and this expression in terms of charge into potential difference. Now comparing equation 1 and 2, what will happen? Comparing equation 1 and 2, we can say that minus Q naught E dr, that is equal to Q naught dV. Q naught cancel out, that is E is equal to minus dV by dr. This is the relation between E and V. Just check, there is a dV by dr, that means rate of change of potential with respect to distance. This dV by dr is called potential gradient. Potential gradient. Okay, that means electric field at a point, is equal to negative of potential gradient. Negative of potential gradient. And what is the significance of negative here? The significance of negative sign indicates the direction of electric field is always in the decreasing order of electric potential. That means here electric potential is higher with respect to here electric potential, because electric field directed along positive x-axis. So with respect to A, point with B has more electric potential. Clear? Now if we write from here, that is dV is equal to minus E dr. Clear? E is a vector form, write it in vector form. E is a vector and dr is also vector, but dV is a scalar quantity, not vector quantity. Now taking integration between 2 point, between 2 position, suppose R1 to R2. So integration dV, and suppose for R1 potential V1 in position, and in position R2 potential is V2. So the limit will be V1 to V2, and here minus integration, that is R1 vector to R2 vector E vector dot dr vector. Now integrate it. dV, that is V1 to V2, and here electric potential, okay, remains same. There is electric potential here constant, write it same condition, that is E dot dr. So the potential difference, that is V2 minus V1, expression will be minus R1 to R2 E vector dot dr vector. This is the expression of potential difference with respect to electric field and position vector. This is the important relation. This is also an important relation. This is equation 2 and write it, this is equation 1. Now, if we consider the two positions, that is R1 and R2, here between two position, if we consider R1, the position R1 at infinity, then what will be the value of corresponding potential? All of you know that electric potential at infinity, at infinite distance from a point charge, electric potential is taken as 0. So when R1 tends to infinity, corresponding potential, that is V1, will be what? 0. And we consider R2, that is equal to R, and corresponding potential V2, that is equal to V. Then simplify equation 2. So V is equal to, this is V, and V1, that is 0. So V equal to minus R1, which is taken infinity, that is infinity, R2, that is taken R, infinity to R, E vector dot dr vector. Clear? So this is the another form. This is the equation 3. Clear? Now, one question is here given. Suppose you have to calculate 3 components of electric fields. That is electric field along x-axis, that is Ex, electric field along y-axis, that is Uy, and similarly Ez. Then what will be the value? From here, you write, from here, dV is equal to minus E vector dot dr vector. Clear? And here electric field and dr, both are the vector quantity, which can be represented as E vector is a vector quantity, so it can be represented as Ex I cap plus Ey j cap plus Ez k cap. Similarly, this is a position vector, so it can be represented as Dx I cap dy j cap plus dz k cap. So electric field along x axis, that is x components of electric field, what is the value? That is dV is equal to minus this expression, that is Ex into I cap only, because we are calculating electric field along x axis, that is x component, and the position vector dr, that is dx I cap plus dy j cap plus dz k cap. Now calculate it. Ex dx, that is Ex into dx, I, there is a dot product, I dot I, what? I dot I, 1, plus Ex dy, but I dot j, 0. Similarly, I dot k, that is also 0, 0 plus 0. So final expression, that is dV is equal to, there is a negative, minus Ex into dx, that is Ex will be minus dV by dx. This is the electric field x component value. Similarly, what is the value of electric field, that is y component and z component? Same method. Y component electric field will be, here this one will be Ey into j cap, then Ey j cap, and this expression will be 0, Ey j cap, and this expression will be 0. Only remaining expression, that is Ey j cap dot dy j cap, that is this expression will be Ey j cap dot dy j cap. So this one will be Ey dy, j dot j 1, there is a negative sign. So sorry, this one is dv. Ey will be minus dv by dy, is the y component of electric field. Similarly, we can say the z component of electric field, that is Ez is equal to minus dv by dz. So this is the forms of electric field. First formula we calculate, that is E equal to minus dv by dr. Then we calculate V2 minus V1, that is equal to R1 minus of 2 R2 E dot dr. Then we calculate V, that is equal to minus infinity to R E dot dr. Clear? Now, using the expression, this expression, what will be the unit of electric field? The unit of potential, that is volt, and the unit of position, that is meter. So unit of electric field here, volt per meter. But in in chapter 1 we know the unit of electric field, that is Newton per Coulomb. Clear? So volt per meter is equivalent to Newton per Coulomb. Yes or no? Obviously yes. Volt per meter. Volt means V, that is W by Q naught. So expression of V, unit of V, that is volt. So unit of what? By charge, that is joule by Coulomb, and there is a meter. And what is value of joule? You know, that is Newton meter by Coulomb meter. Coulomb meter cancel out. That is the unit of electric field, Newton per Coulomb. Also the unit of electric field, that is volt per meter. Both are same. Now take some numericals related to this expression. This is an important vital expression. Okay. Suppose one question given, that is, if the potential in the region of space, that is minus 1 meter, 2 meter and 3 meter, and the potential value given 10x square plus 5y square minus 3z square, you have to calculate three components of electric field. That is, what will be the value of Ex, what will be the value of Ey, and what will be the value of Ez. And you know the formula. The formula of Ex, that is minus dv by dx. So minus d dx of, what is the value of V, that is given 10x square plus 5y square minus 3z square. Now differentiate it. Minus d dx of 10x square, 10 constant part, d dx of x square, so this one will be 2x, d dx of 5y square, this is a differentiation with respect to x, but there is a y, so this expression will be 0, and similarly this expression will be 0, so this value is 20x. And here position given, first position, that is minus 1 meter, so value of x given, that is minus 1, putting this value, that is minus 20 into minus 1, so this expression is 20, and Ex unit will be volt per meter, or you can write Newton per Coulomb. Clear? Similarly, what is the value of Ey? Method same. Ey, that is equal to minus dv by dy, that is minus d dy of, and V, that is 10x square plus 5y square minus 3z square. Now this differentiation with respect to x, so this expression will be 0, this expression will be 0, and we have to differentiate dy by dx, only this part, that is minus 5 constant, d dy of y square, so 2y, that is minus 10y. And according to question, the value of y, that is given 2 meter, just putting, that is minus 10 into 2, expression is minus 20 volt per meter. Then what will be the value of Ez? Same method, calculate. That is Ez formula minus dV by dz, that is Ez is equal to minus d dz of V, that is 10x square plus 5y square minus 3z square. This expression will be 0 because this is function of x, and here differentiate we have to with respect to z. This expression is also same 0. So minus, there is a minus 3, so minus minus plus 3 d dz of z square, that is 2z, so that is 6z. And according to question, the value of z, that is 2, so 6 into 3, the expression will be 18 volt per meter. So the final form, that is Ex 20 volt per meter, Ey, that is minus 20 volt per meter, and Ez, that is 18 volt per meter. Clear? Let's take another example. Suppose electric field E is equal to given A by x cube, x component of electric field given, Ex equal to column 2, A by x cube into I cap. At first you have to calculate the SI unit of A. SI unit of A. Then you have to calculate electric potential. So calculate A is equal to, you can write, just cross multiply, Ex into x cube is the magnitude form, and the unit of Ex, that is volt per meter, or you can write Newton per Coulomb, and x cube, that is meter cube. So this expression will be volt meter square. Similarly, if you write electric field Ex, that is unit Newton per Coulomb, and there is a x cube, that is meter cube, so this unit will be Newton meter cube Coulomb minus 1. Clear? Then second part, you have to calculate electric potential, and you know the formula for calculating electric potential. Here electric field x component given, so the formula is electric potential V is equal to minus infinity to R E vector dot dr vector. This is the form, but here electric field component, that is x component given only, y and z component that is missing. So in terms of R you have to write x only, and the x component value, that is given A by x cube into I cap, and dr, you know the for value dr, that is dx I cap plus dy j cap plus dz k cap, but here only x component given, so dr will be only dx I cap, that is dx I cap, that is minus infinity to x I dot I 1, a constant value, that is minus a outside, dx by x cube, that is minus a, integrate it, when x cube will be upper side, so this one will be x to the power minus 3 into dx, and the formula is x to the power minus 3 plus 1 divided by minus 3 plus 1, limit, that is infinity to x, and putting this limit, that is v equal to minus a, minus 3 plus 1, that is minus 2, that is minus minus cancel out, that is a by 2, and there is x to the power minus 3 plus 1, that is x to the power minus 2, so this one will be x square infinity to x, that is expression will be a by 2x square. Clear? So this is the expression of electric potential here. Okay, so in this class what we learn? We learn that the relation between electric field and electric potential, that is E equal to minus dV by dr, that is the negative of electric potential, that the negative of potential gradient at a point is called the electric field at that point. And what is the significance of negative sign here? The significance of negative sign that indicates the direction of electric field is always in decreasing of potential value. Okay, so this is all about today class. Next lecture will be coming soon, so stay tuned and thank you.